All right, welcome once again, and we'll move on to the next subtopic in this particular topic in chemistry. And today we are going to be considering another very interesting topic. Let me quickly share my slide with you so that you'll be able to see what I have for you today, and what we are going to be looking at. We are going to be looking at together. Just a moment. Let me quickly make this one just a little moment. I want to I want to quickly do this so that you'll be able to see the screen properly. Okay. So today we are going to be looking at separation processes. Separation processes is another very important topic on the JAMB syllabus, chemistry JAMB syllabus, and we want to understand separation techniques. So we are going to be looking at some of the separation techniques one after the other, and we'll define them, we'll give examples about them, and just talk extensively about them, together. Don't forget, my name is Anjoni Oluwafemi Excel, and I'll be your teacher for today. I hold a BSc in chemistry, a postgraduate degree in science education, and a master's degree in environmental and analytical chemistry. All right, having said that, let's go into our learning objective for this lesson. Now, by the end of this topic or this particular lesson, you must be able to specify, you must be able to specify the principle involved in each of the separation method that we're going to be looking at one after the other. Number two, you should be able to state examples for each of the separation methods that we're going to be looking at, and also we'll have to look at how do you apply these basic principles of the separation process in everyday life, So these are our objectives, and these are some of the things that we are going to be considering in the course of this lesson. So please just make sure that you keep focused so that you'll be able to get the very best out of this. All right, let's move to the next one and look at the introduction to this topic. Now, separation processes involves techniques for dividing a mixture into its components or separating a mixture into its components based on differences in their physical or chemical properties. Now, these methods are essential in industrial and domestic settings to purify substance, recover valuable components, or prepare mixtures for further use. So separation processes are very important, and because we find them important in the sense that you can use them for so many things, either industrially or domestically. You find them useful, ranging from how do we purify our drugs, in such a way that we can produce quality medicine that we'll be able to use to combat, health challenges, to just you separating just two mixtures in your house. Take for instance, your child, or maybe your sister, or somebody that is junior to you, gets or even you mistakenly poured water into oil. You will now say, oh, what do I do? How do I go about this? The knowledge of separation techniques or separation method can actually help you to be able to separate, oil and water that you mistakenly mix together. And even going back to your gari that you eat at home, you take at home, when we put gari, sorry for those that may be listening to this and may not know what gari is. Gari simply is just cassava flakes. Now, when you put cassava flakes and you add water to it, you discover that certain things will just come up like dirty component or shaft or something. And then you now get that, the plate of gari or cup of gari, you go to your sink, and then you pour off the dirty or the shafts that is on top of the cassava flakes. What you have simply done is what we call decantation. So these are these are examples of separation processes that we carry out even domestically. So it has found usefulness both in the industry and even in our homes too, in our day-to-day life. And I'm going to be explaining this method one after the other. And I'm not just going to be explaining the method, but rather I'm going to be trying to relate them to your physical environment or your everyday life, finding real life application for these separation methods. Okay. All right, let's move on now. What are the importance of separation processes? Now, one, for purification of water for drinking and industrial use. You know, the water that we drink is purified using certain separation processes, and we're going to be looking at them as we go along. Another importance of separation process is that it is very, very important for recovery of valuable components like crude oil fraction. So the crude oil that is like the mainstay in Nigeria, a very major, commodity that we depend so much on in Nigeria. Without, separation processes, we can not even get that crude, oil refined in such a way that we can get our kerosene out, we can get our gas out, we can get our petrol, and so on and so forth, even up to bitumen that we make use in making roads. So separation processes are very, very useful in recovery of valuable components like crude oil fractions and also for enhancing the quality of food products. We're going to touch on them. We'll talk about crystallization and some other things, distillation, and so on and so forth like that. So it's also important for recycling and waste management. So these are some of the importance of separation processes. Okay, now let's look at the first one now, which is evaporation. Evaporation. I'm very, very sure that majority of us will have, experienced evaporation one way or the other. And basically, evaporation is a separation method or a separation process or a separation technique. And what is evaporation? This is is converting or the conversion of a liquid into vapor to separate it from dissolved solid. So when you have a dissolved solid in a solvent, and you want to separate the solvent and the dissolved and the solid, you want to separate the solvent, you want to separate the solid. One of the methods that you can use for this is evaporation. And evaporation runs on the principle that is based on the fact that liquid evaporate when heated, leaving behind non-volatile solid. So when you heat a liquid, what happens is that because of their volatility, they will evaporate. Now the non-volatile solid now remains in the container that you have. And when you look at the diagram beside me, you can see, that's, make that very good example. You have a mixture of a solid, that has been dissolved in a solution. So a solid and a liquid mixed together to form a solution. I want to separate out, the solid part. A very good example is when you do for okay, we'll get there. Don't let me get ahead of myself. Let me just go slide by slide so that you can be able to understand. So look at that critically. You set the beaker containing the dissolved try to explain what separation methods are, and I've actually um, delved into just a minute, please. Okay, so I've explained what separation method is. I've defined it, and I've also talked about the importance of separation processes. And we want to start talking about each of the separation processes, and the first one we want to consider is evaporation, just like I was explaining earlier. I think I had a network glitch or something, the acting up so terribly. So pardon me. I was is, and I've tried to the best of my ability, I've tried to establish that. Um, I've tried to talk about the importance of separation processes. I've also made mention of what separation processes are, and I was trying to explain what one of the separation process that we have, which is evaporation. And in talking about evaporation, I've defined what evaporation is, and I'm going to define it all over again, just to make up for the bad network. Now, I said evaporation is the conversion of a liquid into vapor to separate it from dissolved solid. Now, when you have a solid dissolved in a liquid to form a solution, and you want to separate the dissolved solid, from the liquid, that it was dissolved in, we said we can use evaporation. Evaporation is one separation method that we can actually employ, and basically what it does is that it operates on the principle that dissolved solids are non-volatile. So, but liquid on the other hand are volatile when they are heated. So what you do with separation is that you subject the dissolved solid to heat, like you can see in the top right and the right hand side of my screen. You can see the diagram that I use in representing that. You can see what happens there. The beaker containing the dissolved solid, or the mixture of the solid and the liquid that has become mixed together into a solution, is heated. And once that is done, what happens is that water starts evaporating. The water gets out of the system. And when you have the water going up, because it is volatile, what you have left is the solid rather. The solid will remain in the beaker, and by so doing, you've separated the dissolved solid from the solvent that it was dissolved in. So that is basically what evaporation is all about. And now, examples of evaporation: separation of salt from seawater. Now, the seawater, we can separate salt from seawater using evaporation. And we can also do what we call concentration of sugar syrup in the industry. We want to have a sugar syrup, a concentrated form of sugar syrup, which is used for so many things, So we can use evaporation for this. What are real life application of evaporation? Example of real life application of evaporation includes, like I said earlier, salt production in salt pans. So when you look for, you go to this to you have a seawater or something, you can actually get the salt out from it. So salt production in salt pans is a real life application of evaporation. Now, drying wet clothes under the sun. You wash your clothes, you rinse it with water, then you put them on the line. After a while, you come back, maybe after 2 hours or thereabout, and you discover that, oh, my clothes is completely dry. There's no more water on the clothes. And the reason is because of the fact that the sun has evaporated or has caused the water content in the clothes to become volatile, that it has taken it up as water vapor. So it is like it has evaporated into the atmosphere, so to speak. So this is a real life application of evaporation. Drying of wet air. You wash your hair and you leave it for a while. I discovered that everything has dried. I was like, wow, this is interesting. The reason is because evaporation has taken place. The wet air, the water in the air that made the air to be wet had gone up. It has volatilized and it has gone up into the atmosphere and then leaving you with your hair being dry. So these are real life examples of what's it called, of evaporation. Tea and other hot drink cooling down. You just get your hot tea and you put it down, and after a while, you discover that the steam keeps going up, and then there's an exchange. Cold air exchanges with the hot air and goes off like that, and before you know it, the drink becomes cold. These are practical examples of evaporation, and I was trying to just use the diagram beside you to differentiate between evaporation being a surface event or phenomenon. It happens on the surface, just like what I was trying to represent with that cup there. And boiling, on the other hand, is something that is not surface alone. It happens throughout the whole of the liquid. So that's the difference between evaporation and boiling. Okay. All right. Let's move on to the next one now. Simple distillation. Simple distillation is another separation techniques that we must be conversant with. And I said simple distillation is simply a method to separate a liquid from a mixture based on differences in boiling points. A method to separate liquid from a mixture based on differences in what? In boiling points. Now, distillation operates under this principle that liquid with a lower boiling point vaporizes first. And this is condensed back into a liquid and collected. Like you can see the setup there. You have the substance to be separated in our glassware there. Now, when you subject it to heat, and what happens is that the liquid with the lower boiling point will vaporize first. And once it vaporizes, it goes through the liquid condenser like that, and then it gets condenses back into normal, liquid, which is the distillate that you can see. And this is just the setup for the simple distillation, and it runs on that principle like I shared with you earlier. All right, now having said that, example of distillation of pure water from salt or impure water is an example of a distillation of a process or a means through which we can use simple distillation. You have impure water, and you want to get, you have sorry please, you have pure water from salty water or impure water. Take for instance, you have a water that is mixed with salt, and you want to get pure water out of it. What you do is that you subject the salt solution, the salt water, you subject it to heat, and then there's a vaporization, and then the water vaporizes and goes back and condenses into liquid or into water back in another container, which we call the distillate, so to speak. And then you have the salt separate and it does not mix like that. Or when you have an impure water, you just subject it to simple distillation, you can actually get pure water out of it because it takes out the water component, condenses it and then drops it as a distillate, and you can have your pure water back. And this is another example of simple distillation is when we obtain alcohol from fermentation mixtures. That's another example. Now, in real life application, one of the ways we apply simple distillation is in purification of our drinking water. The water that we drink can be purified using what? Distillation. This is employed so much even in the Western nation, whereby their water is subjected, some not all, some of their water can be subjected to simple distillation in order to get drinking water, especially for areas that they don't really have, access to water, as they are supposed to. Another application, real life application of simple distillation is the production of spirits in the beverage industry. So you want to produce your alcohols like, your vodka, your gin and so on and so forth like that. These alcoholic drinks can actually be produced using simple distillation. Okay. Now, the next one we want to look at is I call it the senior brother of this simple distillation. Don't mind me. I call it fractional distillation anyway. So basically, fractional distillation is a technique used to separate a mixture of two or more mixable liquid with close boiling point. Now, you discover that the difference between distillation, simple distillation, and fractional distillation is that for simple distillation, it is just used to separate liquid that have different boiling point, that have differences in their boiling point. But for what's it called? For fractional distillation, we use it for separating mixtures that have close boiling point. Let me give you an example. If you have a mixture of alcohol and water, their boiling point is quite close, because if you look at alcohol carefully, you discover that you look at alcohol carefully, you will discover that um, it has a boiling point, ethanol to be precise. It has a boiling point of about 78 degrees Celsius, whereas water has a boiling point of 100 degrees Celsius. It's very, very close. Not only that, you can also use that in the petroleum industry, which I'm going to come to, very, very soon. So when you have you have two or more miscible liquids with close boiling points, you don't make use of simple distillation, but you rather make use of fractional distillation. And now the difference between simple distillation and fractional distillation is because it's just that for simple distillation, there's nothing like a fractionating column that is employed. No, you just subject to it, and then based on differences in their boiling points, the liquid or the solvent part will vaporize, or the one with the lowest boiling point will vaporize first, and then it will go and then condense and becomes the distillate. But for fractional distillation, it is actually different, because fractional distillation operates on the principle of a fractionating column, increasing the separation efficiency by providing surfaces for repeated vaporization and condensation. And that is the principle on which what's it called, fractional distillation operates on. You understand? Now, it is that fractionating column that sets it apart from simple distillation. And that is why it is employed in so many industrial uses, and it gives us pure samples, distillate that are very, very pure. So what do we do? Like you can see the setup in the right-hand corner of the screen. You get the substance to be separated. You put them into appropriate container. It may be a glassware like what you can see there. It can be a big columns, as the case may be for in the petroleum industries and so on and so forth. And then you introduce what we call a fractionating column. The fractionating column basically helps to improve efficiency, separation efficiency, and that is what it does. So the fractionating column will be inserted, and then you have your thermometer like that, and then based on their what's it called, the temperature at which they boil. Once it hits the temperature, take for instance, you have a mixture of maybe probably a mixture A, B, C, and D that have boiling points of 80, 85, 95, 100. Now, if you put them together and they are mixable, if you put them together in a container, you want to subject them to fractional distillation. What happens that once you eat, the one with the lower boiling point will go out first, and they will keep on going out until you get everything out completely. So based on the boiling points, they will come out at their specific boiling point, and then you can get them out as what? As distillates, in a separate container. And this is what we employ in the petroleum industry. I'm going to still touch on this or talk more about this very, very soon. Just hold on as I go along with the class. So that's fractional distillation for you. Now, look at this now. Very, very good. I've given examples of fractional distillation, like you can see on the screen there. So it is used to separate miscible liquids such as acetones and water, chloroform, and benzene. They have close boiling points. So you have to use fractional distillation and not simple distillation. Now, some of the real life application of fractional distillation is that it is used in the separation of crude oil into petrol, kerosene, and diesel. So when you have crude oil, in crude oil, you have so many important substances, very, very, so many of them. So when you get them into a fractionating column, you get them into a what's it called? A fractionating column like this one. What happens is that each of them will come out at their specific temperatures. The first to come out is the refinery gas that have, carbon rate from carbon 1 to carbon 4. It comes out at about 50 degrees Celsius because, that's their boiling point you get. Then the next one is gasoline. Then you have naphtha, and then then you have the kerosene, the diesel, and so on and so forth, up to the point whereby you have your bitumen, pardon me, please, your bitumen, which has a carbon content of about greater than 70. So you have that coming out. Most times it comes out as the last in any this fractional distillation process of crude oil. So it's a very good real life application for fractional distillation. That is the separation of crude oil into its constituents. And so we can have our lubricants, we can have our fuel oil, we can have our diesel oil, we can have our kerosene, we can have our gasoline or petrol, and so on and so forth. So that is that concerning fractional distillation. I hope you're getting the concept I'm explaining. So if you're getting the concept I'm explaining, just do a thumbs up in the comment section. Okay. All right, now. So let's move along and let's talk about sublimation now. Now, sublimation is another separation techniques that is also very, very important. And sublimation is defined as the process where a solid changes directly into a gas without passing through the liquid state. How many of us have seen examples of such before? Whereby you have a substance just changing from solid and it just changes into a gas without going through the liquid state. If you have seen any, put it in the comment section for me. Let me see the comment section. Okay. Now, what principle does sublimation work on? It works on the principle that only sublimable substances vaporizes upon heating. Only what sublimable substances vaporizes on heating. That means that if you have substances like the iodine, your camphor, and so on and so forth, they will sublime. And then when you subject them to heat now, they sublime. And then if you have any other component that is mixed together with them, those components will remain. And you can see a very good example in the right-hand corner where that's a diagram that I use in depicting it. You have a mixture of iodine and sand, and you want to separate a mixture of iodine and sand. How do you go about it? All you need to do is that get the mixture of iodine and sand in a crucible, put them over a Bunsen burner, subject it to heat, and then you can actually get your iodine out because it will sublime, it's sublimable. So it will go off and moves from from the solid into the gaseous, so you can receive it and you can collect it back. And then you have your sand remaining in the crucible that you had the mixture initially. So a very good example is separation of ammonia chloride from a mixture with sand. We have said that, okay. And purification of iodine crystals is another wonderful example. Now, for real life application of sublimation, let's look at some real life application. I talked about manufacturing of mothballs. I know someone was which one is mothballs? Just look at the right hand of the screen. You can see that thing that looks whitish. You can see it a bit. How many of us have seen that before? Yes, you can put it in the comment section. That is what we call mothballs. Otherwise, sometimes we call it camphor. For those of us that have used them before, and most of us have used it anyway, and or we have seen it. Sometimes we put them in our box, that we keep our clothes in. Sometimes we put them, inside our chairs, and all that, and they come in different sizes and shapes, and some of them even come in as they even had fragrance to some of these mothballs too. So you can actually put them in your clothes or your box, the box containing your clothes. You can put them inside your chair or in a place that you just um, that you want them to to dissipate a kind of smell or to repel insects or other items that can come and or moths that can come and destroy your clothes as the case may be. So that's what we use them for, and in real life application anyway. Another very good example is for some of us that have seen the air freshener before. You see your air freshener, like take for instance like this trauma, this week, and so on and so forth like that. They are always solid initially, but after a while, what you notice is that you discover that they become they just it's just as if it vanishes, so to speak. You have a solid substance, and then you just keep them somewhere, maybe in your car, maybe in your restroom, and over time it gives a very nice smell, and you are it was very very nice fragrance, and you are loving the atmosphere whenever you come into the room or you get into your car. But after a while, you discover that that big solid that was there before will just disappear, and there is nowhere to be found. Now, the reason is because sublimation has taken place, and that solid, fragrance or air freshener, so to speak, have been converted directly into what? A gas. And it is that gas that you feel around you, it permeates the environment that you put them in. So these are real life examples or real life application of sublimation. We can also use them for purifying certain pharmaceutical compounds. You can get some pharmaceutical compounds like what you can see with the second slide, the second picture by the side. Before purification, you can see what is happening there. Then after purification, you can also see. So it can also be used for purifying pharmaceutical compounds, and that's concerning sublimation. Okay, so let's move on to the next one and talk about filtration. Filtration. Now, filtration is a method of separating insoluble solids from liquids or gases using a filter medium. We use it to separate what? Insoluble solid from liquids or gases using a filter medium. So we can use a filter paper, and then you separate insoluble solids from liquids. So they are solids that they've dissolved in a liquid, but they're not soluble, and you want to separate them. So what do? You use filtration. Take for instance, if you have you have water and you have sand inside that water, so to speak, you can actually separate by using a filter paper. And all you just need to do is just get a few. You can separate rather by using filtration, and all you need to do is to get a filter paper, just like you can see in that diagram there, and you run the solution through it. The solid component will stay will stay inside the filter paper, whereas the liquid portion will go down. And the liquid content is what we call the filtrates. We call it the filtrates now. Filtration works on the principle that filter traps filter traps solid particles while allowing liquids or gases to pass through. So that is what the principle upon which filtration operates on. The filter that you're using will always trap the solid while allowing either the liquid or the gases to pass through, as the case may be. And a very good example is what you can see there in that diagram that I have attached to this particular slide. Okay, now let's move along now and look at the example of filtration. Example of filtration. So separating sand from water, I've talked about this before, is an example of filtration. Removing impurity during water treatment is also an example of filtration. Real life application of filtration, air filtration in HVAC system, is an example of of filtration. Like what you can see in that diagram is an example of air filtration in the HVAC system. What you see is that you see air that is being supplied. It goes into the HVAC system, HVAC system, and when it goes in like that, there's always a fan that is blowing. Then you see a bag of filter, it filters the air, you know, and then it goes through again the preheat coil. It also go through filtering also, and it goes on like that. And then what you have is now the air that will be coming out will be cleaner, will be free of impurities. So for people that are allergic to certain things, the air that they breathe in or the air that flows around them must be subjected to filtration, so that either pollens or whatsoever it is does not get into the air, and then they breathe it, and it can be very very disastrous to people that have certain health condition. So this is a real life application of filtration during coffee. When you brew your coffee or tea, is an example of a real life application of filtration also. All right, moving along to the next one, we talk about paper chromatography now. Paper chromatography. Now, paper chromatography is a method to separate components of a mixture based on their solubility and movement through a paper medium. So based on their solubility and movement through a paper medium, certain components can be separated. Mostly it's applicable to colored materials, It may not be all the time, but mostly, and you can actually see that in the diagram that is attached to the slide. You can see the separation. You have the paper with spotted with the different substances that you want to separate out. After you have spotted it, you now look for a solvent, a suitable solvent, that you use to elute the substances on the paper, and then based on their movement or their solubility and movement through the paper medium, they will separate out. So what happened is that if you have the red or the what's it called, the blue, having a better solubility or movement through the paper medium, it will move faster or move, very faster and get to the solvent front even before any of the colors. And it will not only be, substance that are colored. Actually, it will be any substance that can be subjected through, what's it called, paper chromatography, in the sense that I have solubility and movements that can move through a paper medium. So it moves out like that, from the origin, like you can see the second diagram by the side here. From the origin, you can see them moving at different pace, at different, speed through the paper. And by so doing, they get separated out. And that is how paper chromatography, that's the principle upon which they work. So I said the principle basically is that components move at different speed depending on their solubility and affinity for the paper. So their solubility and affinity for the paper would determine how their movement will look like. And by so doing, they are separated out into their components. And that is the principle for paper chromatography. So example of paper chromatography, like separating pigments or ink or dyes, it can be used for that. It can also be used for analyzing food additives, some things that we add to our food. We can use paper chromatography to analyze them. We can look for the components as, okay, based on this affinity for this particular paper or paper medium, okay, we are going to separate this out, and then we are going to be able to analyze this. Okay, this is what is in this food additive, this is what is not there, and so on and so forth, like that. And some real life application of paper chromatography includes identifying compounds in forensic science. When a crime occurs, the forensic analyst, can actually identify compounds in forensic in the crime scene using paper chromatography. It can also be used it is used a lot in quality control in food and cosmetics. These are real life application of paper chromatography. All right, so we move to the next one, very similar to paper chromatography, but a bit different because the mode of operation is a bit different from paper chromatography, and we call it the column chromatography. Column chromatography is simply a technique for separating compounds in a mixture based on their adsorption to stationary phase. So for this one, you will have what we call a stationary phase and then a mobile phase, you understand? And if you look at the diagram that I've put beside there, what you will see there is that you have the loaded sample. The sample is loaded into a column, it's loaded into a column like what you can see there. And then after loading the sample into the column, the second diagram, you can see the mobile phase. You have the mobile phase, and then you have the what's it called? The sample separation. The sample starts separating, at this particular junction. The fractions are being collected, from the tip of the column, that was used for the separation. Now, what you discover is that you see in the third one that there's a stronger interaction with the stationary phase that was used. Of the If you look at the or I can call this, okay, let's call it yellow. Yes, the yellow. You can see that it has a stronger interaction with the blue, which is the stationary phase. It has a stronger interaction, and then you have the weaker interaction, which is the one with in green, the sample with green or colored green. It has a weaker interaction. So what happened is that based on their interaction or the affinity for the stationary phase, they will separate out accordingly. And when you look at it, the very last diagram there, which is the um, the fourth and the fifth rather diagram, there you discover that the substance gets eluted over time through the stationary phase. When you have the mobile phase and they just run it through the stationary phase like that, they run it through, or the movement of the mobile phase, which may be a solvent or a gas, as the case may be. This movement of that mobile phase through the stationary phase will separate the samples, and then they will be collected and they will be eluted out. It will go through elution and then it will come out, and it can now be separated accordingly. So basically, column chromatography operates on the principle that components are separated as they travel at different rates through a column packed with an adsorbent material. So that adsorbent material is the stationary phase, and you now run a mobile phase, a suitable mobile phase, which may be a solvent or a gas, as the case may be. You run it through the column and it separates those substances out based on the way they travel, the rate of their, the rate at which they travel through, the packed, adsorbent material or the stationary phase, as the case may be. Okay, so examples of color chromatography is separation of plant pigments, chlorophyll, and so on and so forth. Purification of chemical compounds. It is used in purification of chemical compounds. And real life application, you can see drug sentences and pharmaceutical industries, and then food flavoring and fragrance development. So these are some examples of column chromatography. I hope you're getting the concept as I'm explaining them. If you're getting it, say hey, just say hey in the comment section. Okay, just put hey in the comment section so that I will know that you are following and you're getting the concept. All right, thank you. So we move on now and we talk about simple crystallization. So crystallization can either be simple or or simple or fractional. Yes, fractional crystallization and simple crystallization. Those are the two types of crystallization that we have. So simple crystallization is basically a process in which solid substances develops a crystal structure from a liquid or solution. When you develop, a crystal structure from a liquid or solution, and it entails the transition of a solute from its dissolved state to a solid form, where the solute particles aggregate and organize into what we call respective and orderly pattern, creating a crystal. Now, the big gamma is just represented with that diagram that I put there for you. So what we do with crystallization is, first and foremost, the impure solid is dissolved in a solvent. For us to do simple crystallization, you dissolve what? The impure solid, you dissolve it in a solvent. Now, after you have done that, the next thing is just subject it to heat. By subjecting it to heat, evaporation will take place. The solvent will what? Will go off. Is that also? Now, the third thing is that the hot solution is allowed to cool down. You have subjected to heat. The solvent has gone off. Now, you now allow the hot solution to do what? To cool out, or to cool, as the case may be. Now, in the process of it cooling, the solid appears as pure crystals. The solid will appear as what? As pure crystals. And then the cold solution is poured off to obtain the crystals. So the crystals may be dried by pressing them between sheets of filter paper and so on and so forth. And then you can have shiny crystals and so on and so forth. And you can do, a separation, carry out a separation technique using simple crystallization, following these 4 steps as highlighted in the diagram, beside by the right hand side of the slide. So that's basically what simple crystallization is. And then there's the senior brother of simple crystallization. We call it fractional crystallization. Basically, fractional crystallization is a more specialized form of crystallization that is used to separate different substances in mixtures based on their varying solubility. Based on what? Their varying solubility. Now, it is particularly effective when dealing with mixtures containing multiple components with different solubility characteristics. So this fractional crystallization allows for separation of substances that have multiple components, and that is the difference between simple and fractional crystallization. Then the process involves with repeated crystallization and separation steps to progressively isolate the desired substance. So for fractional distillation, you're not just carrying out a one-off thing that you're just you dissolve the solid, you heat it, and then you allow it to cool, and then you get it. But this one, after you have allowed it to cool, you subject it to another form of crystallization again. You keep on getting until you get the desired substance out. And it can be used for more for substances that have what multiple components. Multiple components. So that's the difference between simple crystallization and what? And fractional crystallization. So what are the real life application now? For simple crystallization, it is widely used in the production of pharmaceuticals, chemicals, and materials to obtain pure solid substances, for production of sugar from sugarcane juice, and purification of salt and organic compounds. For fractional crystallization, it is commonly employed in the purification of minerals, refining of metals, and separation of organic compounds in the chemical industries. So when you want something more pure, you want something more, crystal that is more pure or well formed and the likes like that. You use fractional crystallization because don't forget that it's a repeated action of crystallization and until the desired substance is gotten. Okay, all right, thank you. So we now move on to magnetization. How many of us have played with the magnets before? Okay, you can put it in the comment section. All right, so we've all played with magnets before, and I'm very, very sure that while we were young or much younger than this particular age of ours, we've used the magnet for different types of activities. When I was young, I've used the magnet for to do different types of things. Sometimes you get the magnet. I'll give you an example of some of the things that I did when I was young. Anyway, you can just look for a magnet and then you look for a plastic, and then you put something that is metallic in the plastic, or not even a plastic. Sometimes you even look for a platform. I can put a substance that is metallic or not, that has a iron kind of component in it. I can put it on a particular platform, and I'll now put my magnet under it now, and I'll start dragging the magnet. As I'm dragging the magnet, that substance will start moving, and you can use it to do competition and say, okay, let us see the person that will be able to drop this thing off this platform, faster. And then we start using the magnet, we start moving underneath the substance, and then we drop it wherever we want it to go. And then anybody that does it first, is hailed as the champion and so on and so forth like that. So we can use magnetization for separation as a separation technique also. And basically, I said magnetization in definition now is a physical method used to separate magnetic materials from non-magnetic materials in a mixture. So this technique relies on the magnetic properties of certain substances, making it an effective and simple way to isolate components of a heterogeneous mixture. So what is the principle of magnetization? One, it operates on the principle that magnetic materials are attracted to magnets, leaving non-magnetic materials behind. And that's the principle on which it operates. Okay. So what are examples now? Separation of iron filings from sand. I've done that before. I don't know about you. If you have done that before, just give me a thumb up. Okay, in the comment section. All right now. Okay, so we have separation of iron filings from sand. Then removal of metal contaminants in recycling are examples. What are real life application? It is used in the mining industry for ore separation. You want to separate a ore and it's metallic in nature, or it has a bit of iron or something. You can actually use magnetization to take out all those components and leave behind what you don't want, or as the case, to leave behind what you don't want or what you desire. Vice versa as the case may be. And it's also used in waste management. You can use them in waste management. So these are real life application of magnetization. Okay. The next one is this one that virtually all of us have practiced before, one way or the other, which we call it decantation. So decantation is a physical separation technique used to separate mixtures of immiscible liquids or a liquid and a solid. It involves carefully pouring the liquid from the mixture leaving behind the heavier or undissolved components. I've talked about Gary before. You take a sorry for the non-Yoruba speaking people in Yoruba, land. When you take Gary, that's cassava flakes, by the way. When you pour Gary in water, I say, "Alo yomi Gary yen kuro." Go and remove the supernatant, or what is the top, those dirty particles that is on it. Go and take it off. That's what we call the yomi Gary yen kuro in Yoruba land. For those of us that understand Yoruba, will get the idea of what I'm talking about. So it's just basically decantation, or maybe you mix oil and water together. You can actually separate using decantation because they don't mix together. So one will stay above, the other one will be beneath. So you cannot just get them into a separating funnel. You can get a separating funnel, and once you allow it to stand, what you notice is that you can separate, the oil out. You can separate the water out, as the case may be, and you can see that you can see the sediments, and you can see the water in the liquid portion of that substance being taken off, giving us a clear water, out, so to speak. Now, a very good example of decantation is removing of oil from water. We've talked about that, and also for separating sediment from wine. In the wine industry, it is used in this regard. Now, one thing I want to focus on is the real life application of decantation, and one major real life application of decantation is wastewater treatments. And I got a diagram, beautiful diagram, is it not? Okay. Now, you look at this. What happens is that when all wastewater gather together in the place that it's channeled to gather into, they will allow it to stand. When it stands, it will separate out. You have the sediment or the sludge, it will go down. And then you have the water part, coming out, clear solution of water. What you now do is that you can actually open up a valve and then decant off, using the principle of decantation, the clear water, and then you have the sludge, behind, which you can do whatever you need to do with and process them out as the case may be. So wastewater treatment is a very, very good example of, a process in real life that makes use of decantation, just like you can see from the diagram that I've attached here. So decanting cooking oil in household is also a real life application of decantation. All right. Having said that, let me quickly summarize this lesson. We've touched on filtration. We've described what filtration is. We also gave examples and real life application of filtration. We also made mention of distillation. Not only that, we also talked about the simple distillation and fractional distillation. And we try to explain that the difference between them is that one is used for separating mixtures based on the differences in their boiling point. But if you have a boiling point that is close, you don't use simple distillation, but you use fractional distillation, just like we have explained before. And we talked about the fact that fractional distillation makes use of fractionating columns, which ensures efficiency in separation, and it's because of the close nature of the boiling point of the substance to be separated that we make use of fractional distillation. We give examples of procedures that we can use fractional distillation from, and so on and so forth. So we also touched on chromatography. We talk about paper chromatography. We talk about column chromatography. We touched on these. We explained what they are, the difference between a column chromatography and then a paper chromatography. What they are used for was also touched on. We also mentioned sublimation. We defined what sublimation is, whereby you have a substance that moves from the solid state directly into the gaseous state without going to the liquid state. And so we touched on sublimation, what sublimation is all about, how it can be used to separate substances. Like when you have a mixture of iodine and sand, how can we separate them out? We touched on these. And the last thing we talked about was, I think, decantation, and we explained what decantation is. So with that, we've come to the end of this lesson. And if you have any question on what I've touched on so far, what I've been teaching for so far, you can please drop your questions in the comment section while I evaluate you with these following questions, which I want you to pick up and do and respond to them appropriately in the comment section too. So a mixture of oil and water can be separated using which apparatus? Yeah. Which apparatus can we use for that? I made mention of it when I was talking. So drop your response in the comment section for me to pick it up. Okay. Which separation technique is most suitable for separating a mixture of sand and salt? Yeah, sand and salt. What separation method can we use to separate a mixture of sand and salt? So drop your answer rather in the comment section. Also, which separation technique is most suitable for separating a mixture of sand and salt? So please tell me your answer also in the comment section. I will look at them and respond appropriately to the answers you provided or that you may provide in any way. All right, so which separation techniques exploit differences in boiling point of components in the mixture? So you tell me and just drop your answer also in the comment section. To separate a mixture of ammonia chloride and sand, which method is appropriate? So tell me which method is appropriate. I've talked about that, in one of the separation techniques that I explained. The process of separating a solid from a liquid by gently heating to remove the liquid is called what? I think that was more like the first thing that I touched on in the course of explaining the different separation techniques that we have. So please drop your response also in the comment section for me to see. And the method used to separate a mixture of ethanol and water. Yeah, I also touched on these, and you must tell me if you are answering these questions. Also, tell me the reason why you are choosing that option. So please drop the answer in the comment section for me to be able to pick and then review appropriately. Which technique is used to separate immiscible liquids? Yeah, we've talked about this also. So thank you very much for joining me in this class. I have so many questions. I'll share them with you so you can just drop your questions or your responses in the comment sections, please. Comment section, and then I will do the needful and respond to them appropriately. So if you also have questions based on what I've taught, please feel free to drop them in the comment section. Thank you for listening to this lesson, and thank you for paying rapt attention to all I've discussed. I will see you in the next class. Thank you. Take care.